Okay, so before I get into our first example, I want to give you a physical, and sorry, Summer, you won't be able to see this, but a physical example of what's going on. But if we were to consider the top half of a circle, semicircle, and the shaded region bounded by that here would be like the side of this little object, right? Okay, semicircle. What we're doing today is we're taking that area, that semicircle, and we're going to rotate it around an axis. So if I were to think about rotating it around this x-axis, well, when I take that semicircle and I rotate it around the x-axis and I add all of those up, it would be similar to looking at this getting rotated around this little center. And the result is a three-dimensional sphere. And so what's happening is we're taking this object and we're rotating it around an axis and getting a three-dimensional object as a result. And then what we're going to do is use our calculus, where we can take it and slice it into little slices and add up all those little slices using an integral to find the volume of this. Well, if we follow one tiny little dot, let's just say the dot on the top of this, if I were to follow that as I rotate it around an axis, what shape would I be making as I rotate around that axis? A circle. And so what happens is every time we rotate it around the axis, regardless of what the shape is at the beginning, and I know this is a semicircle to start with, but if you take something, you rotate it around an axis, your slices will always be circles. If I were to follow one little dot around my axis, anywhere along there, it makes a whole bunch of little circles. That's kind of the nice part about our volumes of revolution to start with. I am going to show you, like I said, a three-dimensional rendering on the computer, which again is still two-dimensional, but I'll do the best I can here to help us again one more time visualize this first example. And then I'll show you how I kind of draw it each time in a two-dimensional manner to kind of portray what's happening. So it says, find the volume of the solid that's formed by revolving the region bounded by the lines and curves about the x-axis. So our first example, we're going to rotate our object around the x-axis. The functions given to us this time are y equals the square root of x, the line x equals 4. I'm going to start by drawing this two-dimensionally, then we're going to go to my little visualizer there. So we've got this square root of x function. We've got the line x equals 4, which is a vertical here. And the area bounded by that in our first quadrant here would be all of this. And that area is what we are going to revolve around our x-axis. There are lots of visualizers on the computer. I think I've got a GeoGebra one linked here that we're going to go look at. This is actually kind of a neat one that I could share with us as well, because this particular GeoGebra applet allows you to put in different functions here, and we can even put in multiple functions, which we can utilize tomorrow as we have more than one function. So this one happens to come to us as the same function we were given in our notes, square root of x. They are right now only going from 0 to 1. We were supposed to go from 0 out to 4, right? Ours was line y equals 4. So I'm going to go ahead and change this to 4, and it's going to take me a second here to get the picture to adjust to that. It's a little slow on following here, but bear with me. And so on the left-hand side, we've just got a picture of this. I'm going to zoom out so you can see there's our whole picture. It does not draw that vertical line there at 4, but it stops our picture at 4 there. And what's going to happen is over here, we've got a three-dimensional picture of this. And again, I'm going to try to zoom out here a little bit so we can see that whole thing going on. Oh, and here's the problem with our three-dimensional is it gets a little crazy here. Sorry. I just want to slide over. There we go. Okay. And so what's going to happen as I do this is I'm going to start revolving it, and you'll see that the result happening in our picture as I start revolving this around your axis. You can kind of see that three-dimensional happening, and that looks like kind of like a bell. So it helps you, and It didn't help much because I was throwing it all over the screen there, but so you can kind of see what's happening. Now, we actually don't really need to understand or know that shape. Here's how we're going to attack this. If we come back here, what we want to consider is what axis we're revolving around, and we're going to add in different axes as we look at this, but this particular one, we're going around our x-axis. And what I want you to do is think about, okay, if I were to take my shaded region and like reflect it over that, what would it look like below, so that I can basically see the top and the bottom result. I can't see the three-dimensional coming out at us. It would look like this, right? If I were to like flip it over our axis of revolution. And then what we're going to do is we're going to slice it into those little discs. It's called, all of these today are called the disc method, because it's like we're slicing it in a whole bunch of little circles that are revolving around that axis with us. And so sometimes getting the disc in the right direction is the question mark. Well, what I want you to do is think about making a circle around your axis of revolution, connecting the top function to the bottom function. So if I do that, I'm making a circle around my x-axis, going all the way up to my top function and down to my bottom function. And there's a sample disc, okay, a cross section of this solid. And what we need then for this disc method is the area of one of those little circles. And for a circle, we always need its radius. Your radius will go from your axis of revolution up to or down to, depending on which direction your function is, to your function, right? And so part of our job is to figure out what is that radius, so that we can then go find the area of one disk, so then we can add all of the disks up as we go to find our volume. Okay, so starting with kind of our basic one here, this is very similar to some we saw previously. This length right here, which is the radius of a circle, goes from our axis of rotation up to our curve. Well, that's just from 0 up to the square root of x, right? So the length of your radius would just be the square root of x. And so that then makes our area of one circle pi r squared. R being the square root of x, which means I could simplify this down to pi x. Because that would be going from the axis of rotation to the edge of our circle. The edge of our circle is going to be bounded by that function square root of x. So it's going to be whatever your function is. Very similar to what we did yesterday. All right, so then proceeding into the volume, we have to consider, and we probably should have talked about this earlier, but consider which axis or which direction we are stacking up these little circles, these little disks, right? So I am stacking these up from left to right along our x-axis, right? Smaller ones here towards the origin, bigger ones as we get out towards the end of that shaded region. And we're stacking them up from left to right. And so that tells me that I'm integrating with respect to x, left to right, and that tells me how to set up my integral. So our volume, stacking from left to right, the farthest left we start stacking those circles is 0. The beginning of our shaded region. Out to the farthest right that we'll stack those circles, those disks will be to the edge of our shaded region, which is 4, right? Came from the second line they gave us there. Fill in the area of one disk. And we are stacking up along our x-axis, so with respect to x. And the reason I probably should have talked about that earlier, it does matter to us because it tells us how to write our equations, like in terms of what, and how then to write our radius in terms of what, but we're there. Let's go ahead and write this in terms of pi. So it's like you're sliding your constant of pi out front of your integral. Just do the integral from 0 to 4 of x dx and tack pi on it. How are we doing? Making sense so far? Yes. Yes, it is. Our solids, like, were formed a little bit differently because they changed the shape of the cross sections. When you do a volume of revolution, your cross section will always be a circle because of how it's formed. It's formed by wrapping it around an axis, and that makes a circle. So yes, very, very similar. Yeah, I don't know how else to describe it. What is the integral from 0 to 4 of x dx? Thank you. Yeah, in fact, the visualization may be a little tougher, but the process ends up being a little bit easier, I think, at this point. A little less algebra heavy, usually. Okay, let's do one more. I am going to pop over to that visualizer as you get started with this one, just because I want to one more time show you what it looks like, but I also want to show you that they're not all the same three-dimensional shape and that it doesn't matter to us. It doesn't change our process. So if I pop back over here, this time we are going from the line y equals 2x and out to x equals 3. This applet allows you to change the function if it will respond to me here. So we're doing 2x. We're going to go out to 3. Whoa. So here's our picture, first of all. There's your line, 2x. There's your vertical line, x equals 3. And then over here, oh, I did not look here. There's the same picture, but if I start rotating that function around our axis, this time it looks more like a cone. I zoom out a little bit here. Okay, so not a bell this time, more like a cone. And that's fine. Again, does not change what we do. We still need to just consider what is the radius of our disk, what is the area of the disk, put that into our volume formula. So again, one of the things that I think made you guys very successful yesterday on a very challenging worksheet was kind of thinking through it, not like taking one big bite, but part by part. And first of all, just what is the shaded region that is bounded by the functions they give us. So they give us the function 2x. They give us the function x equals 3, that we are looking at rotating that function, that bounded region, which would be this. There we go. This area around our, again, this time is our x-axis. So if we are going around our x-axis, that again is going to tell me that I'm going to be stacking the disks up along my x-axis. So we want things to say y equals in terms of x. Then I'll reflect it over the line that we are revolving around to kind of get a visual of that whole thing and help me see where the disks are as I draw a circle around my axis of revolution, connecting top function down to bottom function. My radius of that will go from my axis of revolution out to my function. Looking at just a singular disk, our radius goes again from 0 up to our function, which is just a length of 2x. Making the area of this pi times our radius squared, radius being 2x or 4 pi x squared. Now that I know the area of one disk, I can go to my volume. We are stacking these disks along our x-axis. Farthest left that it would start is 0. And the farthest right comes from that second function, x equals 3. So that's how I knew that. Sometimes we have to do like an intersection, which we will look at, but this we do not. Put in the area of one disk, 4 pi x squared, stacking them up along our x-axis. So with respect to x, okay? Grab my calculator, math 9 that. Let's keep all of these except for the very last one. We won't, but this one we'll keep in terms of pi. What do we got? Thank you. And again, we're finding the volume of a solid. These problems don't come to us with like units or anything for us to label, but if it did, if it was talking about like what is the volume of this ice cream cone you just made and they tell you that it is in centimeters, you would now have centimeters cubed, right? Or cubic centimeters. So we can label, we don't need to if it's just no units. All right. What we also need to see today is rotating around something other than our x-axis. So we have an example of rotating around our y-axis and then something that's not a x or y-axis at all. So next one, find the volume of the solid form by revolving the region bounded by the lines and curves about the y-axis. And this time it is y equals 2/3 x and y equals 2. So the equation y equals 2/3 x would go through my origin with a slope of 2/3. And then the equation y equals 2 would be a horizontal line up at 2. Their point of intersection here, if I were to set those equal to each other, or to do substitution here, would be at 2 equals 2/3 x. Let's see, that would be x equals 3. So this would be at 3, 2. If I were to need to find like bounds of integration, I look at where that is. My shaded region that we are rotating is here. But this time, it will rotate around our y-axis. So if I consider, again, reflecting that over my y-axis, it would end up over there. And then I make a big circle around my axis of revolution, connecting my functions. And my radius goes from my axis out to my function. But before we get into thinking about the area of a singular disk, these disks are stacking vertically, aren't they? Okay, which changes how we attack this because we will be integrating with respect to y instead of integrating with respect to x. Are we all seeing that? It's purely the direction that you're stacking your disks. Okay, that's great. That tells me that my bounds on my integral will change from bottom to top instead of left to right. But it also changes how my equation has to go in, and that means it has to be written as x equals in terms of y. And right now it is not. So I bet if we ran to our disk, we would have said that our radius was 2/3 x, and I get that, but I need it to be solved for x. So we need to first, before we move into anything, is take our y equals 2/3 x, 2/3 x, and solve for x. These are the same thing, right? They're equivalent. I just solve for one variable over the other. And because we are going to integrate this with respect to y, we want to think of this function right here as x equals 3/2 y. Now I can come over to the disk, and that does impact our answer because our radius here will go from our axis at 0 over to our function 3/2 y. And our area needs to be in terms of y. Questions? That, I think, will catch us if we're going too quickly and we'd get all the way to our integral and realize we had our equation written in the wrong variable. Okay, so slow down on that. Area equals pi r squared. Our radius, we now know, is 3/2 y. You are absolutely welcome to leave it like that. 3/2 y quantity squared, or you can simplify it 9/4 y squared. Move to our volume. Again, we are integrating with respect to y. So now we got to think our bounds are bottom to top. Lowest point on here is 0. The highest point is our y value of that point of intersection, right? So up at 2 of our area, pi times 3/2 y quantity squared dy. What questions do you have for me right now as we're getting that typed in our calculator? Okay, in terms of pi, What was it? 6 pi. All right. Okay. We have 2 examples left, and we are changing our axis of rotation. So notice we've got a few more functions to deal with this time. It says find the volume formed by revolving all 3 of those, the area bounded by all 3 of those, y equals x squared minus 2, y equals -2, and x equals 2. And this time, notice we are revolving around something that's not an axis. We are revolving around the line y equals -2. Okay, so this one's kind of a basic example to kind of ease us into this. First things first, draw a picture of what we got going on, right? So the equation y equals x squared minus 2 is a parabola. Move down 2. The line y equals -2 is a horizontal line drawn down 2. And the line x equals 2 is a vertical line out at x equals 2. If I draw all 3 of those in there, it will now give me a shaded region bounded by those 3 functions. 3 lines, I shouldn't say functions, they're not all functions. Okay, and also what changed on this one is that we are rotating this time around the line y equals -2, which is down here. So again, if I consider flipping my shaded region over that, it would also show up down here. And the disk that wraps around that axis of rotation, connecting top function down to bottom function, would be here. And my radius would go from my axis of rotation to my function. What changes is identifying our radius, because it is not going to our axis of like 0, x equals 0 or y equals 0. So that's where we have to use this and talk about how we can do this generically as well. So if we look at just one disk, our radius is what we want to focus on right now. And your radius is this length here. Now we haven't really talked about this much because what we were always going to was an axis, but really this length is the difference between these, which is always top minus bottom. But when the bottom was 0, I never really talked about it. It was just the distance to that curve. So when we do this, I want you to really focus on always doing top function minus bottom function, assuming it's not just to 0 like an axis, right? Our top function is that curve, x squared minus 2. Get these out of the way here. And our bottom function, so there's our top function, minus our bottom function. And our bottom function is that line y equals -2. So just -2, okay? Now this one kind of cleans up to like look like things disappear. They're not disappearing, but it does simplify a bit. I would probably not leave it like this. Minus -2 becomes +2. And then x squared minus 2 plus 2 cleans up nicely to x squared. Yes. Right, and actually on the axis, we are doing top minus bottom. If I were to flip back here to this, I am, but this line right here is y equals 0. So we really have been doing that, but subtracting 0 doesn't change anything. So it wouldn't alter my distance, but when my axis moves, it can alter my distance from just going to the function. Does that make sense? So it's not like we weren't doing it before, but there was like really not a lot of reason to talk about it. Okay, and remind me to talk about that same thing vertically as well. So on this one, again, area pi r squared, where our r is x squared, so we get pi x to the 4th. And then our volume, again, no different at this point. Our disks are stacking up along our x-axis still. in that direction. I mean, not centered on our x-axis, but stacking up in that direction from left to right. Looking at this again, we go from left to right, from 0 out to that line x equals 2. So we're going to integrate from 0 to 2, our area being pi x to the 4th, integrating in the x direction. Questions? Okay, this one I don't think turns out as nice, but it's fine. .4 pi, which is fine. You can write that over. It's like a 32 fifths, 6.4, 32 fifths. Did I get that number right? 32 fifths, okay. 32 fifths pi, 32 pi over 5, 6.4 pi, decimal equivalent, I don't care. That's not my concern. Then we'd really never be able to see the board because it gets so bright. Off topic. All right, oh, before we go to this last one, I do want to translate this discussion we just had into integrating with respect to y, because I don't have an example like that. But when you flip to integrating with respect to y compared to integrating with respect to x, it's the same idea. When we were finding the length of our radius, we were really finding the difference between these, but because this line would have been x equals 0, we didn't talk about subtracting the axis of rotation or the left function. So when you do, if you were integrating with respect to y, your radius is your right function minus your left function. Always left to right or always top to bottom when you're doing that. So if I came back over here, just to put generically speaking, with respect to y, it would be right function minus left function for this same idea, okay? And I don't think I have an example in our notes today of that, but just so you can see, if I were to flip my directions, always go right minus left or top minus bottom. Okay, let's do one more here. See one with trig, okay? Region in the first quadrant, bounded by the line y equals 2, below by the curve y equals 2 sine of x, and on the left by the y-axis is rotated around the line y equals 2 to form a solid. Find its volume. So again, we start with a picture of what's going on. We have the line y equals 2, which is a horizontal line. We have the curve y equals 2 sine of x. Now, if you are not sure what those curves look like, I do encourage you to use your calculator to like picture what's going on. But that's a sine curve. You guys know your basic sine curve, right? Starts at the origin, goes up to 1, right? Up to 1 down to -1. Except for at the 2 in front of it, it's got a vertical stretch of 2, or back in trig, we called it an amplitude of 2, right? So it goes actually up to 2 and down to -2. Which means it's actually going to intersect this at its maximum. And then it also says it's bounded by the y-axis. So there's our region. This guy. This time they've asked us to revolve that shaded region around our line y equals 2. Which means, if I consider flipping this over that, it's going to end up being like that. And if I were to consider a disk, I would draw a circle around that line that connects my top function down to my bottom function. I'm going to consider my radius to the function I know, so I'm going to kind of think of it going that direction. Your radius goes in any direction. It's the same. It's a circle, right? But here's the reason why. Again, our axis of rotation is not an axis, not an x or y axis. And so I have to consider my radius length to be the distance between my axis and my function. Well, I want to go the direction I know. So top minus bottom, my top function would be 2. Again, top minus bottom. my bottom function would be 2 sine x. And I have some people say, well, wait a second. It's a radius. Why did you do it that direction and not this direction? I understand that, and it is the same distance each way. However, I don't actually know what function this is, right? It's the reflection of this. I get that it's the same shape, and I get where I got it from, but I don't actually know, and I don't really want to do the work to figure out the equation of that line. So I'm using the equations that I know, which is from here to here. Questions on that? Okay, so then our area, this point's the easy point, right? Our area, pi r squared. I would absolutely not simplify this because you would have to like write it twice in FOIL and everything. So I would leave it exactly like that. A lot of times I simplify, but I would not on this one. And the volume I get when I revolve that, again, I'm going to slow down and say, okay, which direction am I integrating? Our circles are stacking from left to right here. And so the farthest left that shaded region is 0. The farthest right, oh, shoot, I need to figure out this point of intersection, right? I know it's something comma 2, right? I got to figure out where those would intersect. I can go to my calculator. I'm not guaranteeing that you would not have to do this by hand. So if I look at where those intersect, I would probably do substitution. Between the line y equals 2 and 2 sine of x, I can plug in 2 for y and figure out where 2 equals 2 sine of x, or where sine of x equals 1. This is where I would go back to my unit circle thinking and think about, okay, which of those angles gives me a sine value of 1? Do we know? Pi over 2, yep. And since we're just in the first quadrant, we'd stop at pi over 2, right? Pi over 2. 3 pi over 2 is actually -1. It's okay. This one turns out ugly. I'm not going to leave this in terms of pi, so let's just go ahead and, actually, I don't even know, I didn't try it in terms of pi. Assuming it turned out ugly. Just get a decimal equivalent for this one. Go ahead and type pi into your integral. Uh-oh, that table's not agreeing. .935. All right. Okay, so like I said, kind of the one we didn't get was an example of integrating with respect to y, where we had to adjust our radius by right minus left. So do keep an eye out for that if you are revolving around something other than your y-axis, some other vertical line, is that you do pay attention to right minus left for your radius length. We did both of these as top minus bottom because we were going with respect to x, but that's all you did not see. It's still, yeah, it's still units cubed. And like they would never really ask you for units on something if it wasn't like a story problem with like meters in it, built into it. But yeah, understand you're following. So finding volume, so units cubed. All right, guys, your assignments, I've tried to keep them a little bit shorter. You got 6 problems, okay? You do need to complete all 6 with work, okay? Take the time. That's why I'm shortening it a little bit so you can really focus on those and really make sure that you are understanding those.